Ladies and gentlemen, good evening, and let us dig into machine learning, AI, neural network. Yes, it is quite easy when you know the difference. No, it's not, but let us just look at it. First of all, let us look at the concepts. AI, artificial intelligence, it just means that something that tries to imitate human behavior. And a small subset of that is actually machine learning, and here we also have neural network. AI can actually just be a formula. It can just be a complex program. It can also be a simple program, but where the outcome is that it seems like there's human behavior inside the game or the program, and this is exactly what is actually the case with Pac-Man. Pac-Man, it's actually quite a simple formula. All of those four ghosts, they actually have different behaviors, and the formula is actually quite simple, but it is still considered artificial intelligence, because we have Blinky, that is the aggressive ghost. It will just go directly towards the Pac-Man. So that's an aggressive one. Then we have Pinky, that will try to sneak up and ambush from the Pac-Man from the side. Then we have Engin. Engin will just move around randomly, totally random. And then we have Clyde. Clyde would actually try to avoid the Pac-Man, so it will actually try to get out of the Pac-Man's sphere of influence. And just with simple formulas, it actually seems like these almost have a will of their own, or those ghosts. And this is actually artificial intelligence. Just show those simple formulas that those four ghosts actually consist of. Because if you look at the program, then the formulas, the lines of code is not that many per ghost, but what the effects is actually that it's very human behavior. It imitates human behavior, and that's why Pac-Man is actually considered artificial intelligence. Yeah. So artificial intelligence is a lot of things, but the result is that there's something that imitates the human behavior, as I just said. So then we have the subset of AI is the machine learning, because machine learning can try to predict something with a given set of data sets that hasn't seen before from a historic data set that has been trained with. So that means that there might not be a simple formula that can actually calculate what from all the variables what the result should be. Then this is the situation where you would definitely use machine learning. And there are three categories of machine learning: supervised machine learning, unsupervised machine learning, reinforced machine learning. Supervised machine learning is when you have a set of data to train with, then you have a set of data to test with, and then you can actually calculate an accuracy, and then you can sit and configure your layers inside your model. You can configure your model so it actually so the accuracy is increased. That is supervised machine learning. There is someone that has an expert that has to write some test data that can be used for testing the model. So yeah, that is the difference. And you also choose some categories. You choose what you want to look for with supervised machine learning. Then you have unsupervised machine learning. This is a lot of advanced mathematics that actually finds grouping of data, and you do not set up the classification before you start the supervised machine learning. The advanced math will just find these grouping and these tendencies through the data with the math. And that is so. This is not what you usually would see in if you search for artificial intelligence. This is one of the categories that I think that there are the least examples for, and also how to try this out yourself. Let me know in the comments if you have some good examples of unsupervised machine learning. I'll show you an example of supervised machine learning as soon as I've just gone through this theory right here. We have some reinforced learning, machine learning. That is when you try to teach a computer how to play, for instance, Pac-Man or another game. The old arcade machines are very popular to use for reinforced machine learning models, because here you do not need any data to begin with at all. you will have your model, your reinforced machine learning. You will actually have the model to perform an action. So that means that you will actually give it, if it's a game, then maybe you can move your spaceship left or right, or you can shoot. Maybe you have those three options, and then you will have a reward mechanism to the model that will actually tell it when it did something good and when it did something bad. So that means that if it shot an alien, maybe it will get +5 reward. If it dodged an enemy shot, then maybe it will get +1. If it got shot by the alien, then it will get -10 or something like that, or minus 100. So you will set up a reward system for the reinforced machine learning, and then after some time, then the model will become better and better and better, and the action that it will actually take will actually also become more and more sensible, and this will actually seem a lot like, will actually look a lot like human behavior, actually, when you see these reinforced machine learning models playing games. Neural network is being used by both supervised machine learning and also reinforced machine learning. Sorry. You will set up some models, but the simple model that we see right here is a supervised machine learning model, and it's an example of that. We have an input layer, which we have right here. We have some hidden layers, and then you have an output layer. The output layer, that could be a classification of images. So maybe you want some shoes, and maybe the first neuron, output neuron is a shoe. The second one is the category of a jacket, and then you have a pullover, etc., a sandal. So that could be the output. So we have some input. We have some input parameters, some variables right here. Those could be pixel values. If it's a grayscale image, then you could have the grayscale value between 0 and 1, where 1 is totally black, and 1 is white and 0 is black. Then you will put in all of these values right here. And before we do that, we actually need to flatten our data, because the input layer can only take numbers one by one. So that means that if you, for instance, have XY values like you would have for an image, then instead of having XY, then you would start with massaging your data. Then you would massage it so you would actually have a one-dimension array instead of having a multi-dimensional array. So that's usually the first step. You need to know what kind of data you're dealing with. You need to massage it with a flattened layer, maybe, and then you have your input layer afterwards right here. Each of the circles are named a neuron. And from each neuron, there's a connection towards another neuron, and each neuron right here, and each connection has a bias or weight, and the neuron will actually end up with a value. So that means that each of these has a value right here, and then you will multiply that with a weight or bias, and then you would sum up those between all of the neurons in the same layer, and then you will put them into the next neuron in the next layer. And the whole trick here is to find these weights or biases, and that is where there's an optimizer named Adam, for instance, that will go through all of these, thousands of images, and it will try to find the optimal value for this neuron here, 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 to end up with the result. Because to begin with, we're actually training the model. We have the result. We know that the first image maybe it was a sandal, the second image maybe was a shoe, the third image was a jacket, etc., etc., etc. In this example that we are running soon with Keras from TensorFlow and Keras from Google is actually a classification with 10 classes. So that means that we have 10 output neurons, but you can have as many as you want to. You just need to know that that these are just numbers. So of course you have to know that number 0 is a sandal, for instance, right? Okay, so this is a theory. We have neurons. We have connections between the neurons. Each connection can have a bias, and the value for each neuron is calculated by the previous layer's value multiplied by the weight, and then summed up between all of the neurons that actually point to that to the following neuron. So that's the theory. Overtrained models is when you are putting the same data through the model and training it with the same data too much. So then you actually get a model that fits. It's actually also called overfit. Then it actually fits very good to the data that you used to train with. But the test data that you have, the accuracy for the test data will be very low. That is an example of an overfit model. And the way to solve that is actually not to put the same data, to get some more data, or not to put the same data in as many times as you did. That's called an epoch. For each time you shuffle your data and put it into the same model, and that's called an epoch. You can do that a few times, and then you can also cut the lines. Actually, you can cut some of the neurons randomly. That can also help to stop an overfit model. But there's another section of that on TensorFlow's tutorial page right here. We are going to look at this tutorial example right here that says basic image classification right here, and they have some awesome tutorials. Yeah, it's so interesting, and you will actually be you will be pulled in as soon as you have tried the first one. But the first one uses the MNIST dataset. It's a famous fashion MNIST dataset. That means that there are 7,000 grayscale images with 28 times 28 pixels, which means it's awesome and it's excellent for understanding and for running on your own machine on CPU, because all of this training can take a lot of computational power and can take a lot of power. So usually you would actually use a GPU. You can rent GPUs on all of the cloud providers if you want to, but you can also use your own GPU if you have graphic cards in your machine. I'll not show how to do that in this video right here. We will just go through the MNIST example that we have right here. I am using VS Code. Yeah, so let's get started. So I'm using VS Code. I have it right here. When you are dealing with Python and dependencies, you should always create a requirements that the txt file, place it in root, and we need TensorFlow as one library, and then we need Matplotlib as the other library. I use VS Code. I've installed the plugin, the extension in Python extension pack right here. It is awesome because then we get the snake in the left side right here, and then I can actually use Anaconda, which I've installed on my Windows system right here. If you use WSL, then then don't. If you're using Windows with WSL, then put all of your code, put Anaconda on your Windows instance, because or else you will regret it when you start. Because at some point you want to plot out the data that you see with the Matplotlib plotter, and then it's very slow, and it will hang up your system when you try to use the Matplotter. In general, I think it works. It does not work quite well with the WSL, but that's another story. Yeah, so I've created an Anaconda environment named tfdemo, and I used the conda create command to do that, and I have it. I like to always create a package.json file, and then I have my scripts that I run. I have those right here. And I've created this by running conda create, and then I named this environment tfdemo, and then I installed all of the requirements dependencies by running this one right here, conda install -c for conda forge. The reason why I do that is because TensorFlow is not part of the official repository, the conda repository. There's an official repository, and then you have this conda forge where there's a lot of awesome stuff that there's a lot of times when there's something you need to write -c conda forge to get to that repository where you have all the cool stuff that you actually want to use. And then -5 requirements.txt. So I've already run this, so I installed the two dependencies, and I can see those by pressing the snake and then going to my environment right here, and I can see I have TensorFlow right there, and then I should also see the Matplotlib plot somewhere. It's right there. So I'm happy. I'm very happy. I go to my codes, and then I can start by looking at the code. The first thing you want, so in your program, you actually just want to execute this part right here. If you can get a version, that means that your TensorFlow is happy, and you will actually get your that means that you have your TensorFlow dependencies sorted out, and you can actually run the TensorFlow and access the TensorFlow package in the library. So the first thing you want to do, NumPy is excellent for manipulating and massaging data. We actually don't need it when we are looking at the data, so let me just delete it. I've created two files, one to look at data and the other one to train and to test the data. Then we have this matplotlib right here. We use it to print out, to plot pictures from the fashion MNIST from the multidimensional arrays that we get right here. So we have some training images, we have some test images, and we all get those from this load data function right here. Then we have 10 classes. This is just set as a constant right here. So we have a t-shirt, trousers, pullover, dress, coat, sandals, shirts, sneaker, bag, ankle boot, and that is all of those that I just mentioned right here. Those are the output layers which we have right here. Then we can print out the shape. That is something that is quite awesome. Then we can see the shape of our data. We can see the length of our data. The same with the test data. First we have train and test. It sounds a lot like sound very alike, but they are very different right here because we are using. We train a model first, and then we test if our model is okay with some pictures that the model has not seen before. So that's what we do with this test right here. Let us print out one picture. Let us print out one picture, and then we just our comment. Let me just comment the rest of the codes, and let us press play. So what do we get now? We actually get, this is the matplotlib, that's why we need that, so we can get nice images like this. And here we can see that we have a value between 0 and 250. And if when I move the mouse, then I can actually see that I have some XY coordinates. So here this is 10. Here this is 10, 8, and then here I get 224 as the value. So that means that would have a grayscale value, of 224. The higher number, the more white this pixel would be, and the lower the number, the more black it would be. Yeah. And again, we can see the shape right here. That means that we have 3 dimensions. 60,000, that's the number of pictures for training. And then we have the number, this dimension of the picture, 28 times 28. And we only have one color, so that means that or else if we had 3 colors, then we had comma 3 right here. But we only have one color, so that's okay. Then we have 10,000 images for testing when we're done training. So that's quite cool. We can actually already now see what we are dealing with. There's one thing. We want an input number to be between 0 and 1. That is best practice. Then we will not have an overflow error at some point in our model. We could actually end up with that if we have many layers. And it's also just best practice to do that. So you would actually divide your test images and your train images with 255 like this to get a number between 0 and 1. And let me I'll just print out some more pictures, 25 pictures, just to show that we also have that capability from the matplotlib. This time it will be black and white instead of that weird green color. Here you can see we have a dress, we have a sandal, etc. So now we understand our data. So that is why we did all of that. Now the next thing is that we actually want to create a model. So now we understand the data. We do not need to print it out. We know that we need to divide by 255 because we want an input number that's between 0 and 1. And now we create the model. This is the interesting part. So we call TF sequential. Sequential means that it will actually take whatever we have inside this array, and then it will actually set it up in a model as one step at a time from the left to the right. So left to the right, left to the right, each of these layers right here. And what do we have here? First, we have a data massage flatten layer right here. And then we have input layer, then we have some hidden layers, and then we have an output layer. And that is also what we have in the code. So right here we have flatten. Flatten right here, that is just to prepare the data to actually be put into the first, this would be the input layer. And you can see that the input layer is just, it has the same type, dense, just like all of them right here. We're only dealing with dense layers right here. There are many types of layers actually. There are layers that can actually manipulate your images. They can mirror your images, so you would actually mirror them both horizontally, on the horizontal axis and on the vertical axis, and then you would also have convolutional layers that can actually pool together some of the pixels. Maybe it will take 4 pixels at a time, and then you will get all the results by doing that. We do not need that because we have such a small resolution, 28 by 28. But when you come to high resolution pictures, then you need to know about the convolutional layer, and you need to know about a lot of the other layers also. But I will not teach you for the experience of actually going through those tutorials yourself. I might also make some more videos about some of the other tutorials because it's a lot of fun. And then I create. So this is the input. Yeah. So So we have flatten right here, and in the flatten right here, then that's also the input layer. And the input layer actually takes 768. It has 768 neurons, 28 times 28. And then we have the hidden layers right here. So we have 3 hidden layers right here. And we can change those as we want to. We can actually say that this should just be 50. 50. And this should be maybe 100. And this should be 50. And then we want the output layer to be 10 because we have 10 categories. So this one is set. We should not change that at all. Then we will lose some of our categories. Activation reload, do not think about that to begin with. Just do the example. You can read up on the math between it, especially the ADAM optimizer when we come to that down here. Do not think too much about it. It is the optimizer that makes sure that you will get the best weight and bias values in your model. It is when you see those formulas, you will get a little bit tired, but you do not have to understand the formulas, but you have to understand. I think it's nice to understand the purpose of the formula at least, right? Then we have the losses right here, the sparse categorical cross entropy. It's a weird name. And again, you just say, yeah, that's how it is. That's how we calculate the loss. To begin with, you don't need to know about anything about that. Accuracy, that is what we're interested in. That you need to know that. So the accuracy, that is the metric that we want to go for. So we want it to be accurate. And now comes the part. Here we call model fits, and we can go through the data. Sometimes every epoch means shuffle the train data, the training data, and then put it into the model again, and then train once again. And to begin with, if you don't know how many epochs you should choose, then 10 is a good number, I guess. But you can actually see when your accuracy does not improve between the epochs, then it's just waste of time, and maybe you would actually also overfit the model instead. Let's just start with 8. That's okay. So here we have it. Then we get the loss, the accuracy, and then we evaluate against the test images and the test labels. Test labels, that means that those are the test categories that we already know, and this is why it's called supervised machine learning, because we actually given this set, we know exactly all of these images, we know the categories of those. We just want to test them, we just want to evaluate them through against the model. So that is why that's why we're doing this. And then we want to print out the accuracy that we get in the end, and then we have some more code. I will show that in the end. So yeah. Let us run the code, see what happens, and now we're running. So this is epoch 1, 2, 3, 4, 5, 6, 7, 8, and we get an accuracy of 87% right here. If it was totally random, then we would get an accuracy of 0.1, because that means that then we would have it would be right 1 out of 10 times, right? That would, if we roll the dice, then we would actually have 0.1 right here. So that it's an okay model. Of course, room for improvements. We could increase the epochs. We could also add some more layers. That's why the trial and error comes in a bit. Yeah, and let us just run again just for fun. Because then I will I'll show the other code, because let us just run. I just want to show that you can actually play around with these layers, and you can also play around with the epochs, number of epochs right here. We should also set that to something else, but yeah, just set it to something else. Just feel free to do that. Let's see right now. Now we are up at epoch 8, and we're still at. Now we're closer to 88%. So it gave us a little bit, but it was not much. It was not much. And the more layers you add, the longer it takes, of course. So let us just, I think it's, I don't know, it's a bit fun to run this, right? I'll run again now, the epoch 10, and then I'll just show the interest. What I want to show in the end right here is that when we get a prediction, we can actually give us a prediction for this probability method that we have right here. When we get a prediction, then we actually get a percentage per class for how big a chance that this is a shoe, or this is a jacket, etc., etc., etc. So we actually get a percentage of chance that this could be any of the. So now the accuracy is done 87%, and it's much faster this time. So the model didn't get that much better by increasing the number of neurons in each layer. So this is yeah, okay, I forgot to tell you actually. This is neurons in each layer. So we can have 20, 40. Again, we can have, for some reason, I've seen people out on the internet, they usually use something that can be, usually they divide by 2 or multiply by 2 when they change layer. Yeah. Okay, now I'll press play again, but that's okay. So here we have the probability model. I'll show that. Here we will actually get, here we can get predictions from the from the model, from what it just did, and then we will actually see that we get a number per class that we actually are running. And now our test accuracy actually went down after we fiddled with the model, but that's okay. That is okay. So here we can actually see we will get these prediction numbers right here. And then in the end, I'm printing out 40 images, and I say, which class did we predict with the model, and what was the real class name? Because we have the real class name, it is test data. So the real class name is right here, test labels, and then the number of image. And then the way we calculate this is with NumPy. NumPy is excellent for calculating and doing operations on tensors or multi-dimensional arrays. And here we call argmax, and then predictions on the image. This means it will take the largest percentage of prediction from the classes for each picture, for each image, and then it will actually and then it will show it right there. Let us just press run so we can actually see the results. And I'll just delete some of these right here. And let us see what happens now. So before we see all of this, this is picture. This is the first picture. So this is the first picture. Here we get some predictions, and we get some percentages. And E minus 6 means that there are 6 zeros in front of this number right here. So that's a very small number. This is also a very small number, very small number, very small number, very small number, small number, small number, small number, small number. This is quite big because now there's only 1 zero ahead of this number right here. This means that there's actually 94% chance that this is the last category, and last category was ankle boot. So the first picture is an ankle boot according to our model. And if we look at the printout right here, then we can actually see that the real class name is actually ankle boot, and our predictions ankle boot. So that was a Python I did in this area right here. Then we print out 40 images, and then we say what did we predict, and what was the real situation. And the first error we see is actually coat, shirt, sandal, sneaker, coat, sandal. Oh, here it is, sandal and sneaker. So image number 12, that is the first error that we have. We thought it was a sandal, the model thought it was a sandal, but it was actually a sneaker. So we will go back and print that one out just for fun. So I'll go to look at my data. I'll see. Please give me my data. I don't divide. So just move that one. And it was image 12, image with index 12. This is actually not image number 12, it's because we start with 0, so it is the index that we see right there. Let us try to print this one out and see why it was a sneaker or sandal. It could be both, right? It looks a bit like both. It's okay. I excuse my model. I think it's I still like the model. It's still yeah, it's nice. It's awesome. Thank you very much for watching. Have a great evening, and thank you for all your comments. Hope to see you again soon. Bye-bye.